Hello, welcome to my live stream. I hope you can hear me all right. I've tried to lower. Okay, it's been a while. It's been quite a while since I did my last live stream, and the plan for today is to basically continue the implementation from where we left last time. It also took me a little while to figure out what I did last time, and yeah, let's jump straight into it. So in the previous live stream, I was working on this C++ implementation, and the problem I had was I was working on this file system, basically on the FAT file system implementation, and the problem was that I kind of needed to allocate some memory to basically do some memory allocation stuff, and there were some issues. For example, I was trying to create like the file class, which basically implements a block device, and it has methods for reading, writing, and all of those things. And there's the file entry, which is basically the file system, what the file system sees. So basically the file name and maybe some other metadata related to the file. So and then we have the file system class. This is basically the main class, which does most of the stuff that the file system does. Okay, and then we have fat file system, and I kind of started working on this one. And then of course, fat file, which is basically the class which implements all these methods inside the file class. And then I didn't actually write the fat file entry class, and I had this idea of using this file system data basically to have like some memory here that I could use to store file system specific information. I think I kind of found a slightly better idea of how to do this, but yeah, let's start by implementing something which is an object pool. So this is something that I didn't think about last time, but working on the allocators, it kind of came naturally. An object pool is basically I mean, you can have dynamic or you can have static object pools. In a dynamic object pool, you basically have a bunch of objects, you have an array of objects, and then you have some method of allocating from that. And the dynamic part is that that array can grow, so it's basically behaves like a vector or maybe a linked list or something like that. A static object pool means that it cannot grow, so it has a fixed size, but it's a lot easier to implement in an OS when you don't have any kind of memory allocation. So let's do that. I think that might be a good place to start. So I'm putting this inside the mem because it kind of makes sense to put it here. And let's call this object pool.hpp. Let's see. I think I can also make it static. Static object pool. Okay, and we'll also want to have for this to be a template. So T is gonna be the object that we want to store inside this object pool, and it will simply have it's gonna be kind of simple. So it will have two methods, one for allocate an object from the object pool, and then free an object from this object pool. That's it. It's not really that complicated. And then for private, all we need here is to create an array. So for the array, let's also add another template parameter. to specify the size. So let's say size t, pool size. And I think we need std_def, if I remember correctly, for size t. Yes. Okay, and then we have an array of pool size objects. And we will also need an integer to keep track of how many objects we have allocated. So yeah, about this, we also kind of need another piece of information. Okay, so whenever we free an object, it may not be the first one from this array. So what I'm thinking of is to also create another array of booleans, maybe, basically. Is in use. Okay, let's just call it object in use. And initially this will be initialized to all zeros, all false. And whenever we allocate an object, we just mark it as being in use and then decrease the number of objects available. So let's just call this, I don't know, count or size or something like that. Size is fine. Okay. And now for the implementation, this should be fairly simple. In the constructor, I will want to initialize this to 0. And I don't really care that much about these objects. Okay, so let's create the constructor. Okay, why are you complaining? Oh, I forgot the template parameters. Okay, now it's working okay. And yeah, in the constructor, we just want to initialize all these objects to false. So for I think it might be actually more efficient to just use memset or something like this. Let's see if I remember. Okay, I don't have any memset implemented here, but it's fine. Let's just leave it like this. All right, and now for allocate and free. So let's implement those as well. Again, the template parameters. Hello, good morning, everyone. Welcome to my live stream. All right, we can check if we have any object available. So if size is greater or equal to the pool size, then we just return null because we're out of objects. And if the size is not greater than pool size, then we just have to search for an object where this is false. So let's just iterate through all the objects. We can actually start from size. I wonder, it might be more efficient instead of trying to search from the beginning every time to just use size and start from size. So let's do that. In fact, we'll do it another way. So let's create a new variable index, which will be I plus size modulo pool size. So this will just make it wrap around really nicely. And then if the object in use is false, then we found a free object, so we will just mark it as used and then return it. And we return the address. Okay. And yes, we also want to increment size. And I mean, this should not happen, but you know, just in case it happens. Should never happen. This should not be necessary because we're checking here if size is greater or equal to pool size. So there should always be at least one object which is not in use. I can default construct them. You mean this? Like this? Okay. So this one should not be necessary anymore. Nice. I mean, we can also do the same for T. But yeah, that will require that T has a default constructor. But I think that's fine. All right, and this looks good. So last we use the free function. And here we basically just try to get the index. So the index will be equal to object minus the address of objects, and that should give us the index. We should also make sure that it's in the right range. So okay, so if the address of object is smaller than the address of the object's array, then something's gone wrong. And the same if object is greater or equal to objects plus pool size. So we're just making sure it's in the correct range. And then we get the index, and all we have to do is just mark it as not in use. And decrease size. And that's it. This is the static object pool. And now let's see what I've done here. If I remember. I may have forgotten some things. It's been quite a while. Yeah, so the problem I was having is inside the fat file class, I have this read file entry function. And originally, when it was written in C, it would get a pointer to a fat directory entry, and it would fill that structure with whatever it's read. But right now, we kind of want to do this in a more C++ way. So let's not do this anymore. Let's return a file entry pointer. Yeah, so the biggest issue here with this approach that I also was thinking about the last time is when we want to use this file entry object, because if I want this to be because we don't have dynamic cast in in our operating system. This is the biggest issue we have right now. We don't have dynamic cast. So inside the fat file system, whenever we want to open a file, we need to know what type of file it is. We cannot just use file entry. We have to know what kind of file it is. So what I'm thinking of is to kind of change the design a bit here. Instead of having the file system class manage these file entries, instead of having open here, what if we put it in the file entry class? I think that might actually work a little better, because if this is a fat file entry, then it will have the virtual functions and all that, and it will know what kind of object it is. But if we try to use it like this, then this will not work very well. So yeah, I think this might be the best choice right now. So the file system doesn't actually have that much in here, but it still implements a lot of stuff. For example, in the fat file system, you can see that it actually has quite a lot of stuff. It also holds all the data that's needed to read stuff, to read files. Yeah, so let's just remove this. And let's make this file entry class behave more like an object and less like just a simple structure with data. So we can just create a virtual getter for the name. And let's also create a getter for the file type. Yes, this looks good. And let's just set these to 0 because they don't, they're abstract methods. So now let's also create the fat file entry. And it would make the most sense. Yep, so class fat file entry, which inherits from file entry. And of course, we will want to implement those abstract methods. But inside this fat file entry, we will also want to be linked to the file system. So I will include fat file system. And yeah, I'll need to think about what else we need here. Let's see. Inside open, I have this file entry, and I'm just using this fat directory entry structure, and this is basically the structure which contains all this metadata. So what we can do is just add this structure to the fat file entry. Okay, now what else does a fat file entry need to do? It should also be able to open the actual file, right? That's one of the operations. So we're gonna move it from the file system class. We're gonna move it to the file entry class. So we want to be able to open, and we have this file open mode, which I will also move here. All right. Okay, so let's see how we can move it from the fat file system class. I can delete this because it's no longer needed. And here inside open, I basically have an object pool of opened files. And I try to find one which is not opened. So this is exactly why I wanted to implement that object pool class, because now I can just replace this with an object pool. Because this is exactly how I'm using it. Of add file, and I'm using max file handles, which is a constant with how many opened files to keep here. Okay. All right, so what else? So we need to find basically an empty object from this open handle pool. And once we get it, we basically set up some variables here, which are based on that fat directory entry. And we will have to do this okay, so what I'm thinking of is, instead of having this open function, to just have a function that would get an object from this pool. And then inside the fat file entry, I would move this code there. I think that would make sense. Okay, so let's move these to fat file entry.cpp. And yeah, we need to implement all of these methods, and as well as this open function. And yes, we also need to include that file entry.hpp. All right. We will see about the constructor later. For the file name, we just need to return the file names from the directory entry, although there's probably going to be some processing required here. We'll take care of that later. Return value does not match the function type. What do you want from me? Oh, it's not a const char, it's a uint 8. Okay. For the type, we can just use this attribute here. Okay, and now for the open function. Okay, and here we need to get a file object from the file system. So let's add the file system here. And now I need to add a function here. Instead of that open, we want to add a function to basically allocate a file object. Allocate file, and I will also create a release file. I think that might make sense. And all these functions need to do is simply use that object pool to allocate and release file objects. Okay, and for open, this one's no longer needed here. Okay, back to the fat file entry. Now we can call this allocate file function. And then all we have to do is just call open with the file system, and what else does it need? Okay, I think that's it. And yes, we don't need this information anymore because it is stored in the current class. And finally, return a file. And of course, we should also do a check here. If file is null, then we should print an error message and return null. Okay, same here. So if this succeeds, then we will return file. Okay, let's just do it in the reverse. So if this doesn't succeed, then we need to release the files. and return null because open failed. And if open succeeds, then we return file. This makes sense. Okay, let me check the chat a bit. If it's better to make your OS with UEFI or legacy. Well, it kind of depends on what you want to achieve. For example, what I was thinking of is that I also want to try this operating system that I'm making on an older PC with the Pentium 2 era, some compact I have at my parents' home, and I kind of wanted to use that machine for testing. And if you want to use it on an older machine, then yeah, you will definitely need to use legacy. If you're only going to test it in a virtualized environment or on newer machines, newer meaning, I don't know, Core something, Core 2 or something like that, newer, an old i5 or i3, then you should be fine. Most of those will support UEFI. So going with UEFI is a good solution. Yeah, you still need a bit of assembly, but a lot less for you know, with UEFI. The idea in UEFI is that you're basically starting already in the protected 64-bit mode. You don't need to do any kind of switch there. But yeah, you will also need to use some assembly maybe. I can give you some examples. Right here in my OS, I have to use assembly to call BIOS interrupts from this bootloader because I'm using legacy mode. But you also need to set things like setting up the GDT, and you need assembly for that. Setting up the interrupt vector table, you need assembly for that. So if you want to implement a super fast memcopy or memset function, you will also need assembly because I will show you in a future video. I'm planning to make a video about doing graphics, but it will be a while until then. I have some really cool ideas about that. I've also tested this myself, and I've seen how the frame rate then that you can achieve with a simple with like a naive implementation of memcopy, where you just use a for loop, and compare that to something that uses, for example, MMX instructions or something faster like that. It makes a huge difference. You can memcopy stuff. I think if with the normal memcopy, this was in a virtual machine, so with the naive implementation of memcopy, I would achieve something like 15 frames per second. And with the fast memcopy, I would get like 100 or something like that. It was crazy. It was a huge difference. And yeah, the conclusion is that you still need assembly. There are things that you need assembly for to make an OS. It's unavoidable. But yeah, without... if you don't use legacy booting, then you need a lot less of it. How much math is involved in making graphics? Not that much, actually. It kind of depends. There's a bit of geometry involved, you know, because you're trying to figure out rectangles. If, for example, like a hit test when you do a click to see which object is being clicked, but it's not that bad. Some of the more advanced concepts is if you want to do transformations. For example, you want to scale something or you want to move it. I mean, you could do it with a simple function, just a simple subtraction, but transformation matrices are used a lot for that. Usually. If you want to do animation, then you might also have some math there with, for example, all those curves like easing in, easing out. Those might require a bit of math. And I mean, it's not that bad actually. It's not that much. It's not like the 3D graphics. In 3D graphics, there's a crazy amount of math there with quaternions and a lot of advanced concepts. But in 2D graphics, it's a lot simpler. Like X server and window managers. Yes, it's not gonna be X server, obviously. It's gonna be something a lot simpler. But yeah, I am planning to do that in the future. It will take a while until then because we still have a lot of topics to cover. There's the memory management is a huge topic, and this is kind of what I've gotten into right now. I'm working on the physical memory managers video, and it's been a lot of work. I actually have some of those books which are usually recommended, like Modern Operating Systems by Andrew Tannenbaum, and there are a few more. And they don't actually cover the subject that much. They just brush over it. And I was surprised to how little information about physical memory management is in there. And I kind of ended up just implementing a lot of memory managers myself. Yeah, it's gonna be a great video. It's gonna be a really nice video. I will show performance information. I will show a lot of benchmarks to see how these algorithms perform. For example, I have the linked list allocator, I have bitmap, the body system, which is used in Linux. And yeah, I've kind of tried to simulate a lot of situations to see where each one of these will perform better. And yeah, it's gonna be a great video, but it took a lot of effort to make. And it will take a while until we get to yeah, it will take a lot of time until we get to graphics, unfortunately. Can we use Rust? Yeah, we can use Rust, but I started with C++ and I'm gonna continue with C++ because I'm the most familiar. I haven't actually tried Rust. I've just read about it, but I haven't tried it myself, so I don't have that much experience with Rust. And I wanted to use something that I have experience with, which is C++. I use it daily, I use it at work, and that's why. Yeah, we still have a lot of work to do. To connect internet with the OS, yeah, that's a lot of work to get there. The network stack is a whole different topic. But yeah, it will come at some point. I don't know when, but maybe a year from now, maybe more, maybe less, I don't know. How long these videos take to make? I'm thinking that it will take at least more than a year, but yeah. Okay. Yeah, if there are no more questions, let's continue with this implementation. All right, so let's see where we at. We have an error here that we are not implementing the read file entry function. Okay, we will solve that in just a moment. Okay, so we've implemented open, which is great. And yes, now we need to go and implement the... I forgot something here. I was thinking about this directory entry. I haven't set it anywhere. So let's just set it here. And I will take a const reference because this is kind of a big object. We don't want to copy it if we don't need to. And then once this entry is created, again, I also want to use the same I was thinking about using the object pool for this fed file entry. And if we do that, then we will need to have a default constructor here and create like an initialized function which takes in these arguments. But yeah, that shouldn't be much of a problem. All right, and then the directory entry just gets copied from this directory entry that I'm gonna copy here. If I have any infrastructure for virtual memory, not really. I don't have anything right now. I've implemented the allocators separately in a separate project, and I'm gonna present all the strategies. And then I don't know exactly. Maybe I will have to pick one of them. I think I'm just gonna use the bitmap allocator because it's simple and because it performed surprisingly well in all my simulations. It was one of the best performing ones. Porting to other architectures. Yes, I'm planning to port this to either ARM or RISC-V. I'm thinking of getting a device at some point in the future, maybe a Raspberry or something like that, and trying to port the OS to that device. Yeah, but again, this will take quite a while because I really want to get the basics done before I do that, before I jump into that. All right. Okay, so I've implemented the fat file entry, which is basically like a reference to a file on a disk, to the metadata of that file, basically. That's the idea. And then we have the open function, which will go into fat file, and it will call these open functions here. All right. Now, let's see how we can read a file entry. And this is where it gets a bit tricky. Because, yeah, we kind of have to do some manual memory management here, unfortunately. Yeah. I think we have to do the same thing. So I'm gonna go into the file system. There was this data structure, and I'm gonna create an object full of file entries. Okay, I can just call it file entry pool. And fat file entry. Max file handles. Yeah, I think that's fine for now. If it's not gonna be enough, I'm just gonna increase that number. Okay. And same as we did before, we need to create two functions for allocating and releasing a file entry. Yeah, this is the biggest issue here. We have to do a bit of manual memory management. And it will get a bit tricky. All right, I can copy this because it's basically the same. Allocate file entry and just use the file entry pool allocate. And for release file entry, that's it. If I'm using a protected mode FDC driver or BIOS interrupts, neither. I'm simply... So right now I'm in stage 2. In stage 2, I'm not gonna enable memory protection. I'm not gonna enable any protected mode features. I'm just using protected mode to get access to more memory, but I'm still using the BIOS. I'm switching to real mode. I'm using the BIOS to do the file reading, and then I'm switching back to protected mode. That's how my approach has been for stage 2, because this is part of the bootloader and it's not that important here. It's fine to use the BIOS in the bootloader, but in the kernel, I might even skip the floppy disk controller driver completely and just use like an ATA or something like that. So hard drive and maybe CD-ROM, but I might even skip completely the floppy drive. I'm still thinking about it, but... Alright. And I have an error here. Let's fix that as well. So here I am resetting the opened files, and this is not necessary anymore. Okay, now we need a default constructor. So I'm just gonna make this a default constructor and create an initialize function that sets these fields. Yeah, using BIOS interrupts in stage 2. Using BIOS interrupts stage 2 is kind of weird. Yeah, I mean, you kind of have to pick your battles here, right? You have to consider that, okay, we are in a bootloader here. If I was to implement the bootloader completely in real mode, I would just use the BIOS interrupts, no questions asked. But I'm switching to protected mode because I want to have all the extra memory, and I also want to be able to load the kernel at the upper address. So I kind of have to switch to protected mode anyway, or to Unreal mode. That's also another option. But yeah, writing this in protected mode without having to deal with all that weird segment and offset scheme, I think it's a lot better. And I'm also using I'm not implementing full drivers here because I don't want to. I want to be able to read from whatever the BIOS is giving me. If I had to write the drivers, then I would have to write separate drivers for floppy. There's the floppy disk controller driver. Then there's for hard drives, you have to implement one of those ATA drivers, like the simplest one is the ATA PIO mode, but you can also make it more complicated if you want to read faster. If you have an NVMe drive, then you kind of need to read the whole PCI bus and do all the PCI stuff, hardware detection and all that. And at that point, your bootloader is getting as big as the kernel, basically. It's getting big. And the whole idea of the bootloader is to keep it rather small and have it load the kernel. But if you're doing all that in the bootloader, then yeah, you're kind of mixing them up. You're getting a very complex bootloader, and I want to avoid that. In any case, this is mostly for the legacy booting, which is deprecated now anyway, and we will have UEFI at some point in the future. We will also have UEFI support, where we will just use the UEFI functions instead of the BIOS functions. So yeah, it's kind of the same. All right, where's the background music? I don't know, it's kind of hard for me. Some people want background music, some people don't want background music. So I don't know. All right, let's continue. So now for read file entry, as I was saying, let's move that. Instead of having a parameter, we will have a function that returns a file entry. And now for the implementation. Okay, so what do we need to do here? We have this function that reads a file entry and puts it inside a fat directory entry. And all it does is it simply performs a read with the size of a fat directory entry. If you remember from the fat video, a directory entry is simply a structure which... So the way directories work is they are a simple array of directory entries, and we can just read them one by one using this method here. And we are reading 32 bits basically. Okay, so yeah, to read the file entry, we need to first call the read file entry to read it to one of these fat directory entries. So this is the structure from the header. And if this has succeeded, we are going to allocate a fat file entry from the file system. And then we are going to initialize it using the file system, and we also need this entry here. And then we return the file entry. And if this fails, then all we have to do is return null. C++ is overcomplicated. I partially agree with you. I agree that C++ is kind of complicated. But a lot of that complexity comes, yes, from the standard library, because the C++ standard library is insane. It has a huge amount of templates and stuff which make it complicated. And also the language gets a lot of features. In every iteration of the C++ standard, it gets a ton of new features copied from higher level languages. And I agree, but I think for operating system development, it helps a lot. The fact that you can use classes is a huge benefit. You have... Okay, let me show you some code from the Linux source code. Let's see if I have something in history. Nope. Let me think about something from the source code of Linux. I remember looking at the when I implemented the interrupt descriptor table. So the interrupt, what was it called? I have to look in my code. Yeah, the PIC. This is kind of, you can see some of that here as well. So in order to create classes in C, you kind of have these structures which have a lot of pointers to functions. And then if you want to create like a derived version of this PIC driver, all you do is simply change the addresses of these functions to the derived implementations. And I think it's just doing the same thing that C++ does, but in a much more complicated manner, and it's hacky. It's kind of hacky, and Linux does this a lot. Let's see if I can find the PIC. So it was a controller, but I don't remember its name. Okay, so programmable interrupt controller. Okay, 8259. That was the... And let's see some of this here. I remember seeing some structures here. Okay, for example, this null legacy PIC. This is basically a PIC which doesn't implement anything. And this is just like creating a null legacy PIC class. But it's setting everything to... It's just setting all the function pointers. And then you have the default legacy PIC, which implements all the methods. And this is another derived class from this legacy PIC class, so-called class. Linux does this a lot, and I think it just makes the whole design very complicated. It makes everything very complicated. And truth be told, in an operating system where you abstract a lot of things, and you need to abstract a lot of things, and you have a lot of modules communicating with each other, having object-oriented programming, having C++ is a huge benefit. And as you can see, even C does it, but in a very hacky way, because it's C and you don't have classes in C. So why go through all the trouble of doing this when you can just use C++ and just limit yourself to the subset of features which are useful for making an OS, avoiding exceptions and other complicated stuff from C++. Why bother? That's what I'm saying. That's what I've been saying here. Okay. I'm getting a bit distracted here. So I'm gonna implement some more code, and then I'm gonna take more questions if there are more questions a bit later. Okay, reading a file entry. Now, the problem here is that we're not releasing this file entry, and I'm thinking about how to design this. I think the easiest way would be to just create a function here to release it. So creating one in the file class to release this file entry. You created it, you free it basically. Having it, I don't think I want whoever is using this fat file class to have to access the file system directly. So yeah, I think this is the best way to do this. So in addition to read file entry, we will also want to free a file entry here. All right, and Okay. Override. And the implementation is going to be very simple. We just need to call the file system method for releasing. Release file entry of entry. That's basically it. Okay, and let's also add another function here where we are opening a file. Let's also create a release function here. So inside the file entry class, that will be. Why C++ doesn't have interfaces? Yeah, I don't know. Good question. I think an interface is just like what is it called? I mean, in C++ you can have classes that have pure virtual classes which only have abstract functions, and these are basically like interfaces. Yeah, what would an interface have that a class doesn't have? I mean, it would be just like a class, but a bit more restrictive. That's it. Yeah, I think you can just consider it like, given that C++ already has support for classes and also multiple inheritance, then interfaces just aren't. I mean, you can create interfaces with the existing infrastructure. They're just not called interfaces. It's just a language. What was it called? I'm forgetting that word. Just a nice thing in the language to candy. What was it called? I forgot that word. Anyway, not eye candy. It was something else. I'm forgetting. Okay. Here we have a little bit of a problem because this release file entry is expecting fat file entry, not file entry. We can do the unsafe thing and just cast this. Since we don't have dynamic cost, then we don't really have a choice here. All right, let's see what else. We have some errors here. Yeah, so no longer necessary. And the size is an argument. What else do we have here? The name. Don't really have any name here, but we could pass it as a parameter maybe. All right, there we go. Now we have a name as well. Okay. What other problems do we have? Okay, I think this is looking pretty good. Yes, and I'm also gonna add the name here. And that's basically it. Let's take a look in all these classes and see if there's anything missing or if we are all good. We have an error here somewhere, I think. No, we don't. This is misleading. Okay, let's see if we can compile this. Cannot. Oh, fat file entry is abstract because it's not implementing one of the functions. Let's see. Let's see. We have some function which is not being implemented. Which one is it? Yeah, I think no, I forgot to implement this release file. And of course, the arguments are wrong here. In theory, we could do something. No, it's not trying to use the heap. It's one of the functions wasn't implemented. It was this release file function. It wasn't implemented. A virtual function. And yeah, this is supposed to be void, and this is supposed to contain a file. Let's see. And we have the same issue with fat file. One of the abstract functions isn't implemented. That's basically it. Let's see which one. Maybe... Which one is it? Okay, we get some errors here. Okay, let's go to the beginning. Maybe it's gonna say which files have an error. All right. Okay, so file entry does not name a type inside file.hpp. I will just forward declare it to avoid having a recursive inclusion. Okay. Let's see if that solves it. I think it might. Okay, we have another error in headers.hpp. All right, so the problem is fat file does not name a type, so we're probably not including the right files. We're not including fat. the one which contains fat file. But hold on a second. This might be an issue. Hold on. So this file is supposed to contain only the headers, but it's containing this file data, which shouldn't be here. We probably need to either delete or move it. Let's see where it is being used. Nowhere? That's odd. Okay, let's save it in a text editor so I don't lose it. But I think it's probably something that I don't need anymore. All right, fat file system has not been declared in fat file entry.hpp. But we are including fat file system, so what's that about? We might have a recursive. Okay, we don't. Fat file system has not been declared. Oh, so in fat file, it's trying to include fat data, which is trying to include fat file system .cpp. What? Something is weird. Okay, so we have the fat file system. We are including fat file system here, which includes fat data, which includes fat file, which includes fat file system. And the problem is in fat file entry. Yeah, okay, so let's just forward declare it here as well. But we need these, which are include fs file. And for the fat directory entry, we need fat headers. And that should solve it. Okay, one more error. In static object pool. Oh, yeah, we don't have to return anything here. And open. Okay, so this is in the initialize function. Oh, okay, so here we don't have any file name. That's the issue. And this is just the root directory, so the file name is just going to be an empty string. And I think that's it. Almost. Okay, so seek should return a boolean, and it was not returning anything. Anything else? Okay. We still have a bunch of issue. Control reaches end of non-void function. Yeah, we can add a default case here. If this seek position is not valid, then we're just gonna return false. What else? Fat file, no return in the, what is this, seek function. Same as before. I'm not seeing any reason why this should fail, so we can just return true. In open, we have the same issue. So this should return a boolean. Yeah, return true at the end. And open root directory. Yeah, same here. We have quite a lot of errors here. File does not name a type in file entry.hpp. And it is correct. We need to include file here. But it might be... Okay, we forward declared file entry here, so we should be fine including file. All right. Oh, you can see the error because the webcam. There, solved it. Quite a lot of errors. That file was not declared. Where are we? Okay, so we are in a CPP file. We can safely include anything we want here. That file.hpp. Invalid use of incomplete type class file, fat file system. So we also need fat file system here. Almost there. We have fewer errors now. Okay, so now we have issues in stage 2. We've compiled the core library, so all the errors that are left are in BIOS disk. Okay, so we're not implementing seek properly. It should be a boolean. All right, I'm gonna return true here and false otherwise, and this is gonna be a boolean function. Anything else? Address was not declared in this scope here. Yay! We finally fixed all the compilation errors. All right, let's see where we are at here in the stage 2. So, okay, we've initialized everything and we are opening the... We're trying to find the master boot record and reading the partition from that place. And now we should have a partition that we can use. Okay, and now we need to go and initialize the file system. Let's see if we can do that. Open. Okay, read partition. For GPT, yes, probably, but GPT is mainly used in UEFI, so I don't think that's necessary right now. Fat file system. and we initialize it using this partition. Okay, this initialize function is a boolean, so we can verify if it fails. So initialize that file system. And we should do something about it. Okay, critical. We have critical, which will hold the execution. Great. Now that we have the file system initialized, we are trying to find the file that we want. So okay, something I haven't done is to inside this this file system class, now we can actually implement reading files recursively. And the cool thing is that this is gonna work for basically any file system. So that would be great. So let's do that. Virtual file open. And we're gonna pass the whole path. And this is not gonna be virtual. This is not gonna be abstract. We're gonna implement this inside the file system class. Yeah, and I forgot to add that open file mode, which I moved it somewhere else. Let's keep this in where? Oh, it's fine here. Let's just use. Okay, we are including file entry, so we should have file mode, open mode, mode. Okay. Now I remember that I implemented this at some point in the old file system. Let me see if I can find it. In stage 2 old, maybe. Okay, so I have this whole handling of long file names, and I actually started working on this at some point, but I stopped. Okay, here we go. So this is the code that I'm interested in. And I'm just gonna copy the whole code. And let's put this in file system. All right. We will need this variable so we know how big these file names, the name of a single file can get. Okay, ignore leading slash. And then we start with the root directory. And we file entry root equals the root directory from this object. Okay, this is not a file entry, this is a file, but that's okay. And while there's something in the path, we extract the next file name from the path. We will have to implement these string functions that I don't think I added them back. Nope. That's not a problem. We'll take care of that later. Okay. So now we want to find the directory entry of the next item in the path. Okay, and I had this fat find file function, which was taking the name, but I don't think we need this anymore. So find file was basically converting from the format used by fat. If you remember from that video, in the fat file system, files are stored in an 11 character format where the first 8 characters are the file name and the last 3 characters are the extension, and it's padded with spaces in between. So if the file name is shorter than 8 characters, then the rest is filled with spaces, and also everything is in all caps. And this find file would basically iterate through all the file entries inside a directory, and it would also do that conversion. Here we will not be doing that conversion here. We will move that into the fat, somewhere in the fat file system, because that's kind of part of the fat file system. All we care about here is just in the highest level parts of our code. We just want to see if all we care about here is the normal path. And yeah, we will also have to handle those long file names at some point. Okay, so in order to find what we're looking for, we have to start with the first entry, which will be the root read file entry. And while entry is not null, then there are still more entries to be read. So first we are going to check if the current file is a directory entry. Okay, what am I doing here? So I'm iterating through all the So this is the current directory that I'm searching through. And here I am searching for a directory which has the name name. And what am I doing here? So I'm trying, okay, while entry is not null pointer, then we need to check if the entry name matches. So this string compare function that we're gonna implement at some point, if that matches name, then we found it. All right, and yeah, we also have this flag is lost, which will be set to true if we've reached the end of the end of this path. So the last item, after the last slash, basically. Okay, so if the name matches, then we found it. And what do we do with it? So if we have any more file entries, then we kind of need to open that file and okay, so what we will do here is we will close the currently, and of course there's no close function here. Close root, and now we will open a new file. Root equals close and release. That's what we have to do here. And then root we are opening okay, we need to use this entry. So entry open, and this depends. If this is the last, then we want to return this. So we will use this open file mode that we've gotten. But if this is not the last element, then all we need to do is just read. So open mode will be read. All right, so we are opening the new file. And if this is the last, then we will not need to return it. Return root. Because we found what we were looking for. Otherwise, if this is not the last, then we've switched to root. And we're gonna set entry to null. So that we can exit from this while loop here. Okay. If we haven't found it, then entry will be equal to root read file entry. So we're reading the next file entry. And in theory, we should also release the current entry. Yeah, I'm not very happy with how I'm releasing this. I think it might be better to just move this to the entry class. So each object basically can release itself, because all it has to do is just call the file system and tell it to release itself. All right. Okay, so if it's not, so if we haven't found it, we are going to the next one. And we're repeating that until we get either to the end, at which point we're gonna go okay, so if we reach the point thinking a bit. So in this while loop, we are expecting that after this part of the code has ran. Okay, I think I'm just gonna implement this fat find file function. I think it might be easier. Okay, file system.hpp. Find file with a given name inside another file. it's gonna be easier to do this because this function is kind of getting long and ugly. Okay. And let's move this whole loop here. And we can also do some checks. So first, when we enter this function, let's make sure that the parent directory is an actual directory. But we can't because it's already opened. Okay, we're gonna do that check here somewhere. Okay, so okay, we are reading the first file entry, and then until we reach null, we keep reading. Okay, if we have found a match, then we will want to return that match. So we want to return the entry. And that's it. If we haven't found anything, we're just going to continue the loop. So we are going to release that file entry and then go to the next one. And nothing needed here. And finally, we return null because we haven't found anything. And yeah, one more thing about this is that fat is case insensitive, but here I'm doing a case sensitive check. We might have to do something about that, but we will see. Okay, now here we can simplify this. So all we need to do is just try to find the next file entry. So next entry, and in the current directory, which is root, and the name is name. All right. If we found something, then we will need to close the current file, which is, I'm going to put a to do here. Okay, so if this is not the last and this is not a directory, then we just print an error message. Okay, I will do that later. And we return null because this failed. And then we open the new directory entry. So root equals next entry, open, and use the mode. As I was saying previously, if this is the last, we're going to use the argument mode. Otherwise, we're using read. All right. And if this failed, then again, we're going to close and release this root file. And we're going to print a message that we haven't found anything. And we're going to return null pointer. And if everything goes right, we're going to return the root. Okay, there are still a few things we need to take care of. First, as I was saying, I really don't like this approach here, and I'm going to change it. I'm going to have the file release itself. And I can just add a function in file directly. Do I have anything further down? No. All right. So in file, let's add a function for close. Do I not have any close here? No, I don't. All right. So void close and release. So the idea is close basically just closes the file. In fact, this doesn't actually make much sense. I mean, when you close a file, you're not planning to reuse this file object anyway, so we can just have a single function release and that's it. And same here in file entry. All right, and now let's go into fat file and implement this release method. Release file of this. And this will basically make this object not valid anymore. So we have to be careful about this. Okay, and same in fat file entry. Okay, that's basically it. And I can delete this. And I can delete this. And now let's go into file system and call the correct. All right, so let's see, let's think about when we need to delete these objects. So the root directory, okay, so this one is, and here is one place where I'm glad I made that check. So as you can see here, I'm returning this root directory, and this is not meant to be released at all. But if I go to this static object pool, here I am checking that the object is in this range. So even if I release the root, it's not gonna be released. It's not gonna do anything bad. It's not gonna delete that memory or something like that. All right, so if next entry is valid, then if we found the file we are looking for, we want to close the current file and then open a new file. So first would be to close, to release the current. All right, so we are releasing this. And then we are opening the new directory entry, but we also want to release the entry itself after, because we no longer need it. And if we haven't found anything, then we just need to release the root. Okay, and we will also need to do something similar here in this find file function. So we are reading the current entry. And if we are not releasing it, then we will want to release this entry. So entry release, and then we read the next one. And this looks pretty good. All right. I think we've managed this memory all right. Yeah, so what's left to do is implement these string functions and memory functions. All right, let's create a new string.hpp. And I will do the same as I did with the memory functions. So I did this with memcopy, which is implemented in assembly using the repeat instruction. But for string, I'm just going to implement it in C++. Okay, include string.hpp. And I'm going to copy the implementation from the old stuff here. So let's see, string. Okay, so the syntax is a bit different than I was. Okay, find. I'm just gonna call this find because we are searching for a single character. Copy length. And compare. And we will also need some additional memory functions, I think. Let's see if we need anything. I'm not sure. File system. What's wrong? Oh, the source should be const. That's it. All right. This is memory copy. And I think that's it. I don't see any other errors. But we do have some errors, so let's fix those. Add file system, no such file or directory. Did I include this correctly? So it should be in, okay, maybe we have to use core like this. Yes, And the rest should be good. Ah, this is annoying. Yeah, same issue here. Using absolute paths is not a good idea inside of libraries. And we're gonna have more errors anyway, so redefinition of sector size. A previously defined. Oh, here in BIOS disk. Then hold on a second, but why does why does this matter? They're in completely different files. Yeah, anyway, let's just put this inside this class and that's it. We're gonna solve it. This should solve it. Okay, we have some linking errors. It's probably some functions that I haven't implemented, like memset. I can see something about this. In order to what I can do is just use C++ filled, but I also need to redirect from 2 to 1. Was it like this? Nope. There we go. And now we have proper names. And now I probably have a file called one. Yeah. All right. So the constructor of fat file system has a reference to operator new. What? Why would I do that? Ah, okay. So I was trying to do this in the last live stream. I was trying to create like some allocators and stuff. Do I still have those? I don't know. And then I don't have memset. Undefined reference to string char. Oh, yeah. I added these here, but I did not implement. I forgot to copy the implementations for this. So let's fix that. That should solve some of the issues. And now we only have memset and this operator new. So let's start with memset. I have this implementation here. It's not the fastest, but for now we're going to use this one. And I need to create a memory .cpp. I'm just using an underscore to keep it separate from memory.tsm because these will generate the same object files and they will cause issues. In fact, let's just call this one memory ASM. All right, and now let's also add set, which mirrors memset. All right, and now we should have this issue solved, and all that's left is this. But where am I using memset? That's odd. Undefined reference to memset. Where's it coming from? Oh, I forgot something. I need to export using this. I need to use the C, so it doesn't mangle the names, because these functions might be used by libgcc. And that's where it might come from. And I'm gonna do the same here with the string functions. Okay. Okay, it can't find export, which is in core defs. Okay, all that's left is that new operator. And let's think about what I wanted to do here. And I'm trying to remember what I tried to do here and how to fix it. Okay, so basically here, what I was trying to do is to... In the previous live stream, I basically created this memory allocator, stage 2 allocator. And all it is, I think it's called a bump allocator. All it does is simply keep a pointer to some address, and each time you allocate, it basically returns you that address and then increments that pointer. It's a very, very simple strategy for allocating memory. And this one implements allocator. All right. I think I tried to do something about having the new operator, but I'm not sure why this is not working. It might have to be a template maybe or something. Let's see. So it's expecting to have, no, it's just expecting to have a new operator with an unsigned long. And for some reason it's not happy about this. I don't know why. Okay, and here I'm just creating this global allocator. And am I doing anything with it? I'm not doing anything with it. Okay. Let me research this a bit. Okay, so in theory it should work, but for some reason it's not working. It's expecting a reference to operator new of unsigned long. Maybe it's the size T, but size T is unsigned long, so what's that about? Oh, I found a problem. This is an HPP, it's not a CPP, so it's not getting compiled. I'm going to move everything here, and I think only this is needed in the header. And we also need a reference to this allocator class. Okay, and now we can go here into memory, and before doing anything, we're just gonna do set cpp allocator after we include that file. And now we should have new and delete. Okay, redefinition of class allocator. Yes, I forgot a pragma once. Okay, we still have some warnings, but for the most part, it works. Okay, we have some warnings here. So it says that operator new must not return null unless it is declared throw. But it doesn't throw. It just returns null. All right. Making the compiler happy. And now it is happy, and we have successfully compiled. Great. I'm not sure if this is gonna work. Okay, let's go into stage 2 here. And now that we've initialized this file system, let's try to do something. Let's try to open the kernel. But it's definitely not gonna work. And the reason why it's not gonna work is because we haven't implemented that conversion from the FAT file format to this beautiful file names. And that's something we will have to do. Unfortunately, I have to end the live stream. I have to go, and we will take care of that in the next video. And all that's left to do, in addition to fixing up the file system stuff, will be to implement the, let's see what else we had here, the elf reader. This is something we haven't done yet. And after that, I think we can just go to the kernel and do the same there. Now, having this core library is great because we've done a lot of stuff here, and we can share it between the kernel and the bootloader. So for the kernel, most of the stuff that's going to remain to do is going to be the Arch stuff. So the GDT, IDT, and that kind of stuff. The interrupt infrastructure, and then of course the HAL, the virtual file system, that kind of stuff. Yeah, that's basically it. Thank you a lot for watching this live stream. I hope you learned some interesting things. Let's see for other questions. I was writing my kernel in C. Okay, I'm just gonna drag this. So you can also see the questions. Okay, I'm gonna pop this out so it looks cleaner. All right. I was writing my kernel in C, but it became a complete mess. I agree. I switched to C++. Yes, I agree. C++ offers you a lot of opportunities to clean up the code and make things a lot better because you have object-oriented programming. In C, you don't have that, and I think it's a huge advantage. What knowledge do you need for building an OS playlist? Linux and C++. Yeah, that's great. That's a great place to start. For the assembly parts, I try to explain as much as I can. There are other courses which teach assembly, which do a much better job than I do, but yeah, just give it a try. See, if you have trouble with the assembly parts, then you can watch some other tutorials for assembly. Other than that, I think you should be okay. If you know Linux and C++, you have a great, it's a great place to start. It's a okay. If there are no more questions, okay, this is, I always forget to set it to live chat. But yeah, there's no other question. I've already talked about this. Yeah, I think I'm not seeing any new question that I haven't answered. Okay. In that case, thank you a lot for watching. I will continue live streams. I will continue to improve on this until I get it done. There's a bit of work left to do here to basically finish the FAT file system. This has been probably the most complex part of this whole bootloader stuff. I will also do the, as I mentioned, what's left to do is the ELF, and then the ELF file reader, and then test that everything works properly, and the kernel stuff. The next live stream. Yeah, so my goal was to try to do live streams every 2 weeks, but lately I've been really busy. I've kind of failed to get there. I will try to be more, to do live streams more often. Yeah, I can't promise anything, but I will do my best to do them every 2 weeks. Maybe I will try to, do a live stream late at night when I'm bored, when, I don't know, I have some free time. But yeah, right now I'm trying to get that memory management video out. It's been a lot of work so far, and I haven't even started to work on the code. So yeah, you can imagine how much work that has been. Trying to implement all the benchmarks, all the simulations, implementing all the different memory allocators. Do you want to see a sneak peek? I mean, I've released the source code of this project. The source is on GitHub. If you go to the Nanobyte repository, and if you go to the Nanobyte dev, the Nanobyte dev team or something like that. I've set up an organization. So if you go to the organization, you will see there's a physical allocators project where you can find all this stuff. And I've implemented quite a lot of them. A bitmap allocator, a body allocator, linked lists, and I've also tried some more experimental ones using a binary search tree instead of a linked list. But that didn't have a huge advantage in terms of performance. This was an attempt to write a balanced binary search tree, but there are kind of difficult to make, so I cheated a bit. I just used a multi-map, because this is exactly what a multi-map implements. A multi-map implements a red-black tree, which is the binary search tree, which balances itself. And I also have this dual binary search tree implementation where I'm using two binary trees. One for in one of them it's I'm keeping separate the list of free blocks and reserved blocks. And also for the reserved blocks, I'm sorting them by the address, because whenever I want to free something, I'm searching by address. I'm not searching by size. And for the free map, I'm usually searching by size. I'm searching for a block which has a certain size. So this is sorted by size. This is sorted by address. And this actually performs pretty well, but the bitmap allocator still performs a bit better. I have a huge table here with results. I'm still running a few more tests until I can get this done. In the performance data, there's a lot of it here. I'm not gonna go over what all of this stuff means. I've tried to test a wide variety of variables, including the memory size, seeing how these allocator performs with different sizes of memory. And then this is size 1 block ratio, means that basically I thought about the context in which this physical allocator is used. And the context here is I'm using it to allocate frames for the virtual address, for the virtual allocator. The virtual allocator it doesn't care where those physical pages are. It doesn't really need at any point to have blocks that are next to each other. So that kind of completely changes the picture and completely changes how these allocators behave. Because there still is the case when you need to allocate blocks next to each other, which is, for example, if you allocate something it's for hardware I/O, basically, for direct memory access. For example, there's the graphics card will use direct memory access for certain things. The hard drive will also use direct memory access. You just give it a command and it will execute it and copy the data into memory, and it needs a physical address. It doesn't need a virtual address. It uses physical memory for that. And these are the only cases when you need to have big blocks of, I don't know, maybe kilobytes or megabytes of memory next to each other. But for the rest, for all the running programs and all the user space stuff, you just need virtual memory. And wherever you need virtual memory, you don't need blocks to be next to each other. And this is what I'm simulating with this size 1 block ratio. So basically, I'm considering that 75% of all the blocks are size 1, and the rest have a varying size. And I've simulated that using like an exponential random distribution. And this 25, 50, 75 here, I haven't cleaned up the data yet, but I will. This means how full the memory is. So I'm simulating 25% memory full. So every time I'm doing a benchmark, I'm basically simulating a bit of a few allocations. I have a number of iterations, and I simulate random allocations and deallocations until I get to approximately 25% or 50% or 75% of memory used. And as you can see, these do have an effect on how much it takes, how much time it takes to run the algorithms. Yeah, it's gonna be an interesting video, and I'm gonna go into a lot of detail about how I did these benchmarks and about what we can learn from all this. And there are a lot of numbers here, and yeah, it will take a while for me to process them all and get them into a digestible format. Because of how I'm running these tests, I'm having issues with the 1 GB tests. This one, it hasn't finished with all the allocators. It just did like the bitmap allocators, and it ran all night. It's running kind of slow with 1 GB. That's an issue I'm having right now, and I'm trying to figure out how to solve it without invalidating all the other data, because if I just start changing how many iterations some of the stuff runs, then it's gonna invalidate some of the data I have here, and I don't want to do that. I want to avoid that, and yeah, maybe I just have to leave it to run, or maybe try to do it in parallel or something. I don't know. I will see. All right. Any other questions? Yeah, no other questions. Okay. In that case, thank you very much for your attention. I hope this was interesting for you. I hope you learned something. I'm hoping to come back with another live stream in 2 weeks from now. That's the plan, but I can't promise anything. I'm not. Things change a lot, and I might get some more free time in some period and a lot less time in other periods. So it's a bit hard to predict how things are gonna be. Okay then, thank you very much. See you next time and have a nice day. Bye bye.